Okay, let's get started with lecture 8. So today we're going to continue talking about the hydrogen atom, and if there's time, I'll start talking about statistical mechanics. So last time we basically looked at the Schrödinger equation, the time-independent Schrödinger equation for the Coulomb potential, which only depends on the distance r between the electron and the nucleus. And then we wrote the kinetic energy, let's say the K operator, the kinetic energy operator. Again, we wrote it in 3 dimensions. So it was minus h bar squared over 2m times the Laplacian operator. So this operator in Cartesian coordinates, it's simply the sum of second derivatives with respect to x, y, and z. And it can also be represented in spherical coordinates. So it depends on r, phi, theta, and various derivatives with respect to these things, etc. So we had an explicit form for the representation, and the idea was that the solution to the differential equation k plus u of r, this operator acting on some wave function that depends on r, theta, and phi, basically the solution was that we have these energies that depend on one quantum number, but they're degenerate. So there are 2 other quantum numbers. So the energy of a state only depends on n, and we found it to be minus 13.6 electron volt per over n squared. And then we have these other quantum numbers that are related to the angular momentum of the wave function. So n can take the values 1, 2, 3, etc. L can be 0, 2, n minus 1. And m for each L runs from minus L to plus L. So we find for each energy level, we can find more than one state that has that energy, and these are distinguished by the angular momentum. So L is a quantum number that's related to the total angular momentum, and m is a quantum number that's related to the z component of the angular momentum. So let's talk a little bit more about these things. So in classical mechanics, we know that the angular momentum is just the cross product of position times momentum. So it's going to be r cross p. So writing this in terms of components, again, there are some specific operators associated with angular momentum. So Lx, the x component of the angular momentum, the operator that's associated with it coming from this expression is going to be z times py minus y times pz. And then the momenta are what we've introduced before, right? So we know px is minus ih bar derivative with respect to x. Similarly for the other ones. We already know what operators are associated with momentum. We know how angular momentum is related to position and momentum, and then we can construct operators for the various components of the angular momentum. So Ly is going to be, I think it's Actually, this is I had a minus sign error, right? So Lx becomes y times pz minus z times py. Ly becomes z times px minus x times pz. And Lz is x times py minus y times px. And then there's the total angular momentum, right? L squared, which is just Lx squared plus Ly squared plus Lz squared. Okay, so given these operators, what I mentioned that L and M are related to the total angular momentum and the z component of angular momentum, to make that statement precise, basically it turns out that L squared, this total angular momentum squared operator, acting on psi n, L, and m, gives me h bar squared L times L plus 1 psi n L m. So this wave function is an eigenfunction of the angular momentum operator, which means it has a precise angular momentum. There is no uncertainty in its angular momentum. And similarly, Lz times this wave function is h bar m times psi n L m. Okay, so let's try to take a look at some visualization of these wave functions. So this is a free Java applet. You can play with it yourself, and there are also molecular orbitals. There are some other interesting applets, so that's the website. So the way these are represented is basically like the wave function is going to be at every point in space, it's going to be some complex number, right? And you can think of it in terms of a magnitude and a phase. So every complex number, you can write it as rho, let's say, or r, times e to the I phi, right? That's a way of representing all complex numbers. So this is basically showing you the r, the magnitude of the wave function, and then the color is related to the phase. So this wave function that all has the same color is basically like there's no phase apart from the phase that comes from the dynamics at e to the minus I energy times t. Otherwise, all at every point in time, if you look at snapshots, you don't see different colors because the wave function for L equal 1 is just a real wave function up to that dynamical phase. And so this is a really simple wave function. Basically, you have like some spherically symmetric wave function for the ground state. Doesn't matter if I rotate my coordinates. And the probability kind of decays as you move away from the center. And for L equal 1, we only have one state. For n equal 1, because L runs from 0 to n minus 1. N minus 1 for n equal 1 is 0. So we only have one value of L. And that's the only state we have. So the ground state is unique, right? It's not degenerate. Okay, so let's go to the next energy level. N equal 2. So this has an energy like the first one was minus 13 electron volt. This is minus 13 over 4 electron volt. Slightly over minus 4 electron volts. So now n can be 2, which means L can be 0 and 1, right? So if L is 0, again we have a spherically symmetric wave function, but now we see it's no longer real, right? As we have different colors in it, so the phase is changing. And then you can look at it from different angles. Again, we have the spherical symmetry for this wave function, which is related to the total angular momentum being 0. So if you have a finite angular momentum in some direction, right, it's like physically you expect some kind of a rotation around that axis. So there's something particular about that axis. But if you're spherically symmetric, there's no particular axis. So we see this. Now let's go to L equal 1. And now we see different states. So now kind of you have your weight is distributed, is kind of, you have two centers for high density around the origin. This is the m equals 0. So no net angular momentum in the z direction. Somehow around the z direction, it seems you have two things that are symmetric around the z direction. I go to m equal -1. Now we have this orbital that has angular momentum around the z-axis. And again, it has a structure of having two places for high density. M equal 1 is going to be very similar. Let's look at another higher state here. So we can go to L equals 0. Again, spherically symmetric, has kind of a more nodal antinodal structure. This typically happens when you go to higher energy states. If I look at L equal 1, next total angular momentum, we can get more complex structures in these wave functions. M equals 0, m equal 1, or -1, m equal 1. So yeah, so they become much more complex as we go to higher energies and higher angular momenta. So let's look at something really crazy, n equals 16. Wow, that looks really complex. Let's look at some high angular momentum, let's say 9 and 6 and 5. And so yeah, so these wave functions can be really complicated, right? But basically, like this R, how bright it is, right? Brightness has to do with the magnitude of the wave function. So if you square it, it's like the probability of finding the particle somewhere. So if you have an electron in this particular high energy orbital, there is this really intricate structure for the probability of finding the electron in various places around the nucleus. All right. So we talked about these various wave functions, which are also known as orbitals. But there's also a very important kind of experimental consequence of these energies, right? So basically, the idea is we're saying the stationary states of an atom can take only these discrete energies. So now it has a direct consequence for the frequency of photons emitted by an atom. Because how does an atom emit a photon? Well, energy must be conserved, and the atom can only be in one of these eigenstates, one of these stationary states. So in order to emit a photon, it must be initially in some high energy excited state, and then it decays to a lower energy level, and it emits a photon whose energy is precisely the difference between the energies of these levels, right? So photon emission so let's say you're initially in some level with energy Em, right? And there's some lower energy level somewhere. So let's call that, or let's call them E initial and E final. So the atom is initially here, and there's no photon, and then what happens is a process can occur where the atom kind of decays to this low energy state. And a photon gets emitted with energy h nu, where nu is the frequency of the photon. And of course, to have energy conservation, we need to have E, the energy of the photon, which is h nu, to be equal to EI minus EF, right? So here the total energy is h nu plus EF, photon plus atom. Here the total energy is EI, the energy of the atom. There's no photon. And EI must be equal to EF plus h nu, the energy of the photon. So now, if these energies only take certain discrete values, in the case of the hydrogen, let's say En is minus 13.6 electron volt over n squared, where n is 1, 2, 3, etc. Well, that means that light emitted by this atom will only have certain frequencies, right? So if I look at the frequencies, the frequency of a photon must be minus 13.6 electron volt divided by h times, let's say, 1 over n initial squared minus n final squared. Right? And that also implies that the wavelength of photons emitted by this atom will only take certain values, because we knew that lambda times nu is just the speed of light. So lambda is going to be c over nu, or 1 over lambda is going to be nu over c. So 1 over lambda will take these values divided by the speed of light. And that's precisely what happens. And this was actually one of the experimental observations before quantum mechanics was developed. People were looking at the light emitted by different atoms, and they saw these reproducible spectra. Light was emitted at very precise frequencies. So for example, for the hydrogen, there were like around maybe 100 nanometer. There were 4 bands, something like this. And then, there were some other precise frequencies observed around here, maybe 400 nanometer, around 500. And then the next one would be over 600. So these were observed at very, very precise wavelength. And it was a mystery, like, okay, where is this coming from? And we can tell where it's coming from after the development of quantum mechanics, right? So the stationary states of an atom, which come out of solving the time-independent Schrödinger equation, take certain quantized values, and then once an atom emits a photon, it's because it decayed from a high energy state to a low energy state. And then the difference between these energies becomes the energy of the photon, which is related to its frequency. Okay. So let's look at an example. So this is example 7.2 from Harris' textbook. So what it says is the atom in a sample of hydrogen or the atoms in a sample of hydrogen, are all in their ground states. Okay. Far too cold and slow to bump one another into higher levels. Okay, so you have a very cold hydrogen gas. You can be confident that pretty much all the atoms are in their ground state, n equal 1, energy minus 13.6 electrons. Then a beam of electrons accelerated through a potential difference of 12.3 volt is directed at the atom. So hydrogen atoms in ground state hit by a beam of electrons. And if they're accelerated by a potential of 12.3 volt, it means that each electron acquired an energy of 12.3 electron volts, right? Each with energy 12.3 electron volts. What wavelength will the hydrogen atom emit? So that's the question. So let's think a little bit about the physics of the problem. So we have these hydrogen atoms, right? They're being hit by some electrons. So you can have a process where the electron scatters off of the hydrogen atom and loses some energy. So fast, let's say low energy. And then it can become high energy. The atom can be excited, it can be bumped into a higher energy level. And the electron leaves, but it has lower energy, or it's slower. Right? So the energy can give some of its, or the electron can give some of its energy to the atom. Okay. And the atom can get excited again. The atom is kind of pinned into certain energy levels. So in the same sense that it's guaranteed to give up energies that come in certain chunks corresponding to these differences between various natural levels, it can also absorb energy in those chunks and get excited to one of those levels. So it will absorb some of the energy of the electron. Okay, so let's see what are the levels it can get excited to. Well, we know that n equal 1, so has E1 equal minus 13.6. N equal 2 has E2, which is minus 13.6 over 4, right? That's 2 squared, so that's minus 3.4 electron volts. So there's definitely enough energy in that electron to excite the atom from n equal 1 to n equal 2. Then n equal 3, E3 is going to be minus 13.6 over 9, right? That's 3 squared. And that's minus 1.51. So again, minus 13.6 plus 12.3 gives us, what does it give? Gives us minus 1.3 electron volts, right? So this is minus 1.5, so it's lower than that, right? So there is enough energy to excite the atom to this level. But n equal 4, we'll have E4 equal minus 13.6 over 16, which is less than 1, 85. So that's not enough. So available energy gives you like minus 13.6 plus 12.3, which is minus 1.3. So we can excite, like these electrons have enough energy to excite the atom up to any energy that's lower than minus 1.3 electron volt, right? So we can't get this, and we can't have excited states with these energies. That's what the electrons do. And then the atoms, when they are in those excited states, they can decay to lower energy states and emit photons with some corresponding energy. So the process is if it's here, if it gets excited to the first excited state n equal 2, well, we only can have a process where we go from 2 to 1, right? That's one allowed process, and it gives a photon, excuse me, with a certain energy. If it gets excited up to the third level, well, we can have 3 to 1. We can also have 3 to 2. And there's nothing else. So basically, we're going to get only three types of three frequencies rather of photons that can be emitted after we excite this gas of atoms, this cold gas of atoms, with electrons of certain energy. Well, we can only get certain excited states, and each of those excited states can only decay to certain levels that have a lower energy. So here the energy of the photon will be E2 minus E1. And in this case, this is minus 12.1. In this case, E3 minus E1 is going to be plus 10.2 electron volts. And finally, E2 or E3 minus E2, that's going to be 1.9 electron volts. So immediately from these energies, we can plug in for the speed of light, then an age, and calculate the various wavelengths. Okay, so lambda is hc times E, right? E over h is the wavelength, so c times c over the E over h is the frequency, and c over the frequency is the wavelength. And hc, it turns out in useful units, electron volts times nanometer, that's 1240 electron volt nanometer. So using this number, we can get lambdas in nanometers that are kind of useful. So we find lambda 2 sorry, there's these should be switched, right? E2 minus E1 must be smaller than E3 minus E1. So let me correct that. So that's 10.2. And this is 12.1. So lambda for this process 2 to 1 is going to be 122 nanometers. For this process 3 to 1 is going to be 103, and for this process 3 to 2 it's going to be 656 nanometers. Okay, so the lower the energy difference, you get a higher wavelength as expected. All right. So let's move on to a new topic that turns out to be kind of related to this. So we're talking about statistical mechanics in chapter 9. So when we were talking about quantum mechanics, basically, let's take a step back. So we talked about the time-dependent Schrödinger equation that governs the dynamics of quantum systems, and then we talked about stationary states that give rise to time-independent probabilities for measuring various observables. Then we had a couple of examples. So we had a few examples in one dimension. We talked about a more realistic example in 3 dimensions, the hydrogen atom. And this program can go on. So if you have a more complicated atom, or maybe a molecule, again, you have more electrons, right? So you would write an operator corresponding to the energy of the system. So if you have 2 electrons, for example, you will have 2 kinetic energy terms, and there's going to be the interaction, the Coulomb interaction also between the electrons. So as you can imagine, this scheme can become exceedingly complicated as you go to larger systems. And ultimately, if you're talking about a piece of material, let's say you have a metal, maybe you have 10 to the 23 electrons, right? So writing a Schrödinger equation for all of these, where everything talks with everything, is not going to be feasible. But fundamentally, the solution to that huge equation gives a huge wave function for this piece of metal, and all the properties of this piece of metal, at least if it's in the ground state, for example, is determined by that wave function. So in solid state, in condensed matter physics, basically one comes up with various methods and techniques to make sense of the properties of this big many particle wave function for all the electrons in the system without doing a microscopic ab initio calculation of writing just this continuous Schrödinger equation for all the atoms. So basically one comes up with various approximation methods to address this problem. But fundamentally, all of materials physics boils down to the Schrödinger equation at some level. Except in practice, maybe that's not a good way to gain insight about the behavior of materials. So one thing that we didn't talk about much so far is the role of temperature, right? So we said, take the hydrogen atom, for example. We find these energy levels, E1, E2, etc. The ground state is the lowest energy possible state, and then you have a whole bunch of excited states, an infinite number of them. So somehow one expects that if you are in equilibrium at some temperature, the higher the temperature is, the more excited states you have, right? Consider a gas of atoms. Okay, so classically, if you go to, let's say, 0 temperature, then there's no energy, so all of them are kind of, it's not going to be gas, they kind of freeze into some structure. So if you just have one atom, which can have these low energy and high energy states, well, there is this intuition that the hotter this system comprised of these atoms is, more likely you are to have the excited states. So the example we just worked out, for example, we had this assumption that initially everything is in the ground state because it's really cold, right? And then the only transitions you can get is from the electron beam hitting the atom and exciting it. But what if initially you're not really cold, right? So statistical mechanics is one way of kind of making sense of of that problem. So let's start by a simple example, a simple thermodynamic system, and try to make sense of some of the concepts that appear in statistical mechanics. Okay, so consider line 1. Consider a two-sided room and imagine you have 4 particles in this room. Okay, so yeah, the room, imagine there's like a partition in the room, so there is a right half and a left half. And let's think about the number of ways of putting a certain number of particles in this room such that, you know, you have, let's say, n left particles here and you have n right particles there on the right hand side, right? So n left plus n right is equal to n. So somehow intuitively maybe we expect that in general, if, you know, if half the molecules are on this side and half the molecules are on that side, it's a more likely scenario than if all the molecule or all the particles are in one side of the room, right? If you just think about the air molecules inside a room, most of the time, pretty much all the time, basically like any small box you put in that room, yeah, roughly the number of molecules in that box is going to be proportional to the volume of the box, right? So if you take half of the room, roughly half of the air molecules are going to be in that half. But why is that, right? There's nothing that disallows fundamentally the particles from all kind of collecting in one half of the room. So it boils down to basic counting and certain scenarios being more likely because there are many more microstates that give rise to that scenario. So so one way to think about this is, okay, so what are the possibilities? So let's do an example. So n equal 4, for example. Okay, so nr can be what? nr can be 0. So all of these 4 particles can be on this side. Okay, so if I give some label to these particles, 1, 2, 3, and 4 are all here. Now let's say nr is 1. So what are the possibilities, right? So there are more possibilities because I have 4 choices for the 1 particle that's on the left-hand side, right? So I can have 1, 2, 3, and 4 is on this side. Or I can have 1, 2, 4, and 3 is on this side. Or I can have 2, 3, 4, and 1 is on this side. Or 2 is on this side, and I have 1, 3, 4. Right, so I find 4 possibilities. If you have nr equal 2, well, there are more possibilities. It's going to be 6 of them, it turns out, right? So you can have either pick, let's say on one side you pick 1 and 2, or 1 and 3, or 1 and 4. So that's 3. And then you can pick the ones that don't have a 1, so it's going to be 2 and 3 and 2 and a 4, and the ones that don't have a 1 or 2, so that's going to be 3 and 4. So we're going to get 6 different possibilities. So somehow that has a larger number. So let's think a little bit about counting these. So how can I think about think about the number of ways. Well, it's basically the number of ways of selecting n left objects out of n objects, right? So for example, here I chose one object out of 4 objects, and I had 4 different ways to get this partition. So how do I think about the number of ways of choosing, let's say, n left from n? Well, the first thing I want to mention is kind of something called the permutations, which is the number of arranging n objects, right? Number of ways of arranging n objects. Okay, so if you have 3 objects, I can do 1, 2, 3. I can do 1, 3, 2. I can do 2, 1, 3. I can do 2, 3, 1. I can do 3, 1, 2. I can do 3, 2, 1. Right? So there's going to be 6 ways. One way to count this is, I'm saying I can imagine like 3 placeholders, 3 boxes. And for the first one, okay, how many choices do I have? Well, it can be 1, it can be 2, it can be 3. So I have 3 choices, right? It can be 1, 2, and 3 for the first one. Then for the second one, for each of these choices, I have 2 choices, because if this is 1, so 1 is gone, 2 and 3 are left. So I have 2 more choices. The second one can be 2 or 3. If 2 is gone, the second one can be 1 or 3. And if 3 is gone, the second one can be 1 and 2. And finally, the last one, there's no choice left. So basically, yeah, if 1 and 2 are gone, only 3 is left. So see, one way to count all of these is kind of branching structure. You just have a certain number of branches, and then they all kind of branch off, etc. Is to say, well, here I have n choices for the first one, right? So in this case, n is equal to 3, so I have 3 choices. Then the second one, the number of my choices is n minus 1. And then we go all the way, and for the last one, it goes all the way to 1, right? Because I've already put in n minus 1, so only 1 is left, and I'm left with 1 choice. So this is n factorial, right? So it's 1 times 2 times 3 up to n. So that's the number of permutations of n objects. Okay, so I have another way of thinking about this. So let's say number of ways of choosing let's say nr out of n. Let's call this C of n and nr. Okay. So I don't know what that is, but somehow I can relate this to the permutation. So suppose again I have n objects, right? And I know the whole permutations is n factorial, but let's now construct this in a different way. Let's choose nr of these. So for example, take an example, nr equal 3. So let's say the first 3 boxes, I choose nr out of n particles, and I arrange them in this half. So here I have nr, here I have n minus nr. So the total number of arranging these n objects is, well, you can imagine first you choose nr out of n. So I have that many possibilities for what are the objects in the first, let's say, nr boxes. And then for each of those, we can arrange these nr objects nr factorial ways. And the remaining objects, n minus nr objects, in n minus nr factorial ways. So now, dividing this expression by the product of these factorials, we find the C of n and nr. The number of ways of choosing is just n factorial over nr factorial over n minus nr factorial. This is known as the binomial coefficient. It's a coefficient that appears in the expansion of 1 plus x to the n, like the coefficient of the term x to the nr, for example, will have a coefficient like that. So let's see if this works. So for example, here when nr was 0, we had just one configuration. We can think of it as 4 factorial over 4 factorial over 0 factorial. 0 factorial is 1, so that's 1. In this case, choosing 1 out of 4, I have 4 factorial over 3 factorial over 1 factorial. 1 factorial is 1. 4 factorial is 4 times 3 factorial, so that becomes 4. In this case, let's see what we're going to get. So I'm going to get 4 factorial over 2 factorial over 2 factorial. So it should be 4 times 3, right? That's 4 factorial divided by 2, and then divided by 2. So it's going to be 6. And the way we counted them just by hand, we had these 6 possibilities, right? So I can have, on this side, I can have 1, 2, and the rest on the other side, or 1, 3, or 1, 4, or I can have 2, 3, or 2, 4, or 3, 4. And there's no other possibility. Okay. So that's the binomial coefficient. And okay, so for this small number, it's not quite clear why a scenario where half the objects are in one half and half the objects are in the other half is the most likely one. But we can kind of, so that's just n equal 4. And we can calculate these numbers and kind of plot them. So this is one example. Let me draw this. So let's say n is equal to 40. So as a function of another notation for this notation, another notation is just this. You put n upstairs in 2 parentheses nr. So the number of ways of choosing nr out of n, which has that expression. So if I plot this nr as a function of nr for a fixed n. So in this case, let's say I pick n equal 40. So what I'm going to see is, well, 40 is here. And the maximum always occurs at 20, at half of it. So the maximum in this case is going to be a huge number. It's 1.4 times 10 to the 11. And basically like around 10, I think it's like a decay like that. Around 10 it's really tiny. So it looks kind of like that. If you do n equal 400, n equal 400, now, say here you have 200, half of it, 100 is here, basically where it's really tiny is around there. So this peak, of course the maximum is huge, it's 1 times 10 to the 119. So as you go to larger and larger numbers, the ratio of the number of ways where these particles, where nr is, for example, equal to n over 2, to the total number of ways for the sum of all these different possibilities, right? Sum of all of those. That ratio becomes larger and larger. So this distribution becomes narrower and narrower, and it becomes more and more unlikely for a state to be found in one of these configurations here, where nr is much smaller or much larger than n/2. Okay, so at this point it may not be yet clear why this counting exercise, how it relates to temperature, how it relates to what we motivated before, like what is the state, what is the average energy, etc. But basically this kind of counting and a fundamental assumption that all microstates are equally likely is a foundation for statistical mechanics, which allows us to gain much better understanding of the finite temperature behavior of physical systems. So this is a good place to stop, and we'll continue the discussion in the next lecture.